Hello everyone, welcome to today's class. In this lecture, we are going to discuss about one particular form of limit that is done by using the L'Hopital rule. Okay. So there are certain conditions. First of all, you should understand when to use this rule, and then we'll see how to use this rule. The application part is very simple as such. So what this rule says, like if you have some limit x tends to a fx by gx, okay, and suppose you are solving this and you are getting 0 by 0 form, okay, or infinity by infinity, both are applicable. So in that scenario, you can rewrite this as limit x tends to a f dash x by g dash x. Given that g dash x is in the denominator, so that should not be 0. Okay. In case this is again generating limit x 0 by 0 or infinity by infinity, again you can solve this by limit x tends to a by getting the double derivative, and so on. Okay, 3 times, 4 times, how many times you want to differentiate, you can keep on differentiating as long as you get the limit. So but you have to understand the conditions. Condition is like this is applicable on 0 by 0 form or infinity by infinity form. Okay, and the function of course should be differentiable. Fx and gx should be differentiable. We are calculating the limit at a, so at x equal to a, they should be differentiable. And I think that's it. All right, let's look at the questions now. Limit x tends to a, x raised to power a minus a raised to power x upon x raised to power x minus a raised to power a. Okay. Now, if you look at this question, of course, solving it with the standard form, it's very typical. Okay. But what you can see is when we put x as a, so a raised to power a raised to power a, denominator becomes also a raised to power a raised to power a. So this becomes 0 by 0 form. So yes, L'Hopital is applicable. Okay. So we'll differentiate the numerator and the denominator. So if we differentiate numerator, so x raised to power a differentiation is a x raised to power a minus 1. A raised to power x differentiation is a raised to power x log a. Denominator x raised to power x differentiation, what you do is you take this separately, y as x raised to power x, then calculate y dash by taking log. Okay, so log y is x log x. This is logarithmic limit, so you'll have to solve that separately. Y dash by y is 1 log x plus 1. So y dash is y 1 plus log x. So y is x raised to power x 1 plus log x. Okay, so whenever you have slightly complicated differentiation, you can solve them separately. So write down here, this is x raised to power x now. So differentiation is x raised to power x only, 1 plus log x. And now a raised to power a is constant. So differentiation of a raised to power a is also a constant. Sorry, a is constant, so a raised to power a is also a constant. That means the differentiation is 0. Okay. Now let's put the limit to be a. Let's see if we can solve this after applying L'Hopital. If we put a, it becomes a raised to power a minus 1 minus a raised to power a log a upon a raised to power a 1 plus log a. We multiply this, we get a raised to power a, and then you can take common from the numerator, 1 minus log a upon a raised to power a 1 plus log a. A raised to power a raised to power a cancels. So basically the answer is 1 minus log a upon 1 plus log a. If you want to simplify this slightly further, you can write log 1 as log e minus log a, log 1 as log e plus log a, and use the property of log. In subtraction they will become division, log e by a, upon in addition they will become multiplication, log ea. So that is your answer, or depending on the option this could also be the answer. Okay. All right, let's look at the next question. It's saying let f of a is equal to g of a is equal to some k, and nth order derivative of fx and gx exists. Okay. If f limit extends to a, f of a g of x minus f of a minus g of a fx plus g of a upon gx minus fx. This limit is 4. Find k. You have to find the value of k. Okay. So weird looking question. Function is not given. It's just that the function is saying that f of a and g of a, they are equal to k. So these are constant values sum. Okay. Now if the limit exists, we can directly first of all check if x is tending to a, this becomes f of a minus fa minus g of a f of a. Sorry, this is f of a g of a. If we replace x by a, okay, denominator becomes g of a minus f of a. Okay, g of a, f of a, they are equal, so they'll cancel, so this becomes 0. Numerator, if you look at also, this g of a minus f of a again becomes 0, and these two cancel, so 0 upon 0 format. So L'Hopital is applicable, so let's differentiate. If we differentiate numerator, it becomes f of a is constant, so leave it. G of a is g dash x minus f of a, again constant, differentiation is 0, minus g of a, leave it, constant in multiplication with fx, differentiation is f dash x, g a differentiation again becomes 0, and the denominator differentiation is g dash x minus f dash x. The limit is still tending to x tends to a, and this should give us 4. Okay, I've applied L'Hopital on the given expression. From these two expression, what we can do is, like, f of a and g of a, they are both equal, and they are equal to k, na? So I'll take k common. Okay, so basically this value is also k, this value is also k, so I'm taking k common, so I get g dash x minus f dash x upon denominator is also g dash x minus f dash x equal to 4, and limit x tends to a. These two cancel each other, so what do we get? K as 4. Okay, so the moment we apply L'Hopital directly on this question, it solves itself automatically. Okay, all right, next question. Limit x tends to a raised to power x minus x raised to power a upon x raised to power x minus a raised to power a is minus 1. Find value of a. Now this is like the first question we solved. I think in the first question it was x raised to power a. Okay, so this was x raised to power a, this was, and then a raised to power x. So the first question was, if I convert this into first question, I'll have to take negative common, and this becomes first question. We have already solved this, that's why I'm going to use the result of that. You know you have to differentiate numerator and denominator. After that, what do you get? Minus of 1 plus log a, sorry, 1 minus log a upon 1 plus log a. Okay, after differentiating and putting the value of x as a, you get this, and this value is given as minus 1. Negative negative cancels. Okay, so let's solve further. So 1 minus log a equal to 1 plus log a. 1 cancels, so basically 2 log a is equal to 0. So log a is 0. If log a is 0, a is e raised to power 0. That's 1. That's the answer. Okay, so they can manipulate the question like this also. Instead of directly asking for limit, they can ask find the value of a. Okay, they have given this as minus 1 here. They can give us minus 2 also, minus 3 accordingly, or anything. All right, next question. Limit, standard question of limit. Limit x tends to 1, 1 plus log x minus x upon 1 minus 2x plus x square. Okay. All right. Now if you look at the numerator 1 plus log x minus x, so two different kind of functions are there. We have to solve the limit. Let's put x directly as 1. Let's see direct substitution if works or not. So log 1 is 0. This 1 becomes 0. So this is becoming 0, and denominator also 1 minus 2 plus 1 also 0. So 0 by 0. So L'Hopital is applicable. Let's differentiate. Differentiation of 1 is 0 plus log x differentiation 1 by x minus 1 upon 0 minus 2 plus 2x. Differentiating numerator and denominator both. The limit should still exist. Limit x tends to 1. Let's see if direct substitution works now or not. If we put x as 1, still numerator is becoming 0. Denominator is also still 0. So still not applicable. Differentiate again. Numerator and denominator. Limit x tends to 0. Minus 1 by x square upon 2 differentiation is 0, only 2. Now if we put limit as 1, this gives us minus 1 upon 2 as the answer. So yes, so you have to keep on differentiating unless and until you get the answer. Okay, so this time we have to differentiate it 2 times. One time it was still getting answer as 0 by 0 because x was tending to 1. So I again differentiated it and I got the final answer. All right, next question. Limit x tends to 0, tan x minus x upon x square tan x. Now this is a good question. Why? Because you'll learn that in order to apply L'Hopital, you have to keep differentiating until you get the limit. Now first of all, let's check whether it is 0 by 0 or not. X is 0, so 0 minus 0 is 0. Denominator is also 0. So yes, directly differentiate. So sec square x minus 1, differentiation of numerator. Denominator you'll have to use uv. So differentiation of x square is 2x tan x plus differentiation of tan x is x square as it is sec square. And limit is still x tends to 0. So sec 0 is also 1. So still numerator is 0. Denominator is still 0. So again differentiate it. So limit x tends to 0. If we differentiate sec square x, it becomes 2 sec x, and then differentiation of sec x is sec x tan x. Okay, and denominator, let's use uv here, uv here also. So uv here, so I get 2 tan x plus 2x, tan x differentiation is sec square x, plus here it is 2x sec square x, then plus x square, then sec square differentiation is 2 sec x into sec x tan x. Getting lengthy. All right. Let's write down this slightly simpler way. Second sec becomes 2 sec square x tan x. Denominator, let it be as it is, 2 tan x, 2x sec square x. Actually 2x x square x, 2x sec square x now. So let's combine that. Both the terms have same. So it becomes 4x sec square x plus x square, 2x square sec square tan sec square x tan x. Okay, I hope this time should get the limit. X is tending to 0. So tan 0 is 0. So numerator directly becomes 0. Denominator is 0. X is there, 0. X is there. Still 0 by 0. So again differentiate. Okay. So this question gives you the idea that yes, sometimes even the L'Hopital questions are lengthy. Although this is usually used to, solve the questions quickly, but sometimes it takes time. So now again uv in the numerator. So 2, let it be sec square differentiation, we already know 2 sec square x tan x, and then sec square as it is, tan x differentiation is sec square x. Denominator will be lengthy. 2 tan x is 2 sec square x differentiation. 4x sec square x, uv again you have to use my part. uv here, uv here, uv here. UVW will have to use. My goodness. Okay. 4x differentiation is 4 sec square x, then 4x as it is. Sec square differentiation we already know. 2 sec square x tan x, then UVW. I think it will be better if I write the UVW in the next line plus here. Okay. 2x square differentiation is 4x, remaining 2 terms as it is. Then 2x square as it is, tan x as it is. Sec square differentiation is 2 sec square x tan x. Okay. Plus 2x square as it is, sec square as it is. Tan x differentiation is sec square x. Whoa, very lengthy. Now let's see. I hope this time it should come around 0 by 0. Not 0 by 0, I hope. If we put in the numerator 0, so this becomes 0 into anything is 0. Sec 0 is 1, so at least numerator is not becoming 0. So hopefully denominator will also not become 0. Sec 0 is again 1, so 2 sec 0 again 1 4. This is x is here, so the moment we put x0, anything is multiplication is becoming 0. Here also again x is 0, so everything becomes 0. X is there, x square is there, again it becomes 0. X square is there, again it becomes 0. So 0 0 0 basically. So yes, the denominator is not becoming 0. So the answer for this question is 1 by 6. Okay, once. I think we missed this 2. This 2 will come here. So this 2 will come 2 by 6. That becomes 1 by 3. Yeah, that will be the answer finally. All right, this is done. So this is a perfect question to understand that you have to keep differentiating unless and until you get the final limit. As long as 0 by 0 is there, you can directly differentiate, use the L'Hopital. And the format is applicable on infinity by infinity also. But only these two formats, not anywhere else. All right. Let's look at another question. Limit x tends to 0, log x log sine x. Now this is problematic slightly because you don't have a denominator. So what I'll do is I'll generate denominator. How? I'll write this as limit x tends to 0 log sine x upon 1 by x. And now let's solve this. What is the differentiation of log sine x? So log sine x differentiation will be 1 by sine x. Let's check first of all whether the limit is 0 by 0 or not. Sine 0 is 0, log 0 is minus infinity as such. So basically infinity by infinity form it is. So still applicable. Okay. So yes, so we can differentiate. So 1 by sine x into sine x differentiation is cos x upon 1 by x differentiation is minus 1 by x square. Okay. So this becomes cos by sine becomes cot x and upon minus 1 by x square, and limit is x tends to 0. Okay. Now I think we can solve this limit. If we rewrite this as minus x square cot as 1 by tan x, I think we can solve this. I can write this as minus x into x upon tan x, and this x by tan x I can rewrite it as tan x by x. Tan x by x becomes 1. So minus limit is still x tending to 0 minus x. Now I think we can do direct substitution. So putting x directly as 0, we get minus 0. There is no such thing as minus 0. So 0 is the final answer. All right. Fine. So you can use it to solve some questions of trigonometric limit also, and I think you can derive your limit x tends to 0 sine x by x. Okay, this is also 0 by 0. You can check why it is coming 1, because if you differentiate, this is 0 by 0 form. First of all, you can differentiate numerator, it becomes cos x. You can differentiate denominator also. This becomes 1. So now put x as 0. So this is cos 0, that's 1. Okay. So you can use your normal limits also to solve some of the question, but you remember the format is applicable on 0 by 0 form or infinity by infinity. Okay. All right. Fine. That covers your part for the L'Hopital rule. Okay. So practice these questions. These are important. Usually limit questions do touch around this concept a lot. So just get clarity. As such, it's very simple to use. Okay. All right. That's it for this lecture. See you in the next class. Good day, everyone. Bye.